Am I audible? Hello? Hello? Am I audible now? Priya, can you call person? Hello? Hello? Is the mic working? Hello? Hello? So everyone here is for the CS769 course, right? I'll try and speak until the mic gets set up. So I'm Ganesh Ramakrishnan. Welcome to this course, Optimization and Machine Learning. I would like to put a disclaimer up front that this is going to be at least this version of the course is going to be more project heavy than the previous offerings of the course. And that's of course thanks to the boom in large language models. Not audible. Okay, thanks. Is this better? And also because the flavor of optimization today is also quite dynamic based on the advances in large language models. But more about this as we progress. So a little bit on why take this course, some motivation, prerequisites, and then we'll talk about the course logistics, give examples of continuous and discrete optimization in machine learning. This part is going to be rather breezy this time. So, of course, why optimization in machine learning? Needless to say, optimization is everywhere, right from the problem of deciding where to place bulbs in a classroom like this to where the AC ducts, right, have to be placed. So optimization is pretty much there everywhere. Sometimes we resort to heuristics. This course will try and take a more principled approach. Now, mathematical modeling, where does optimization exhibit itself? So the most famous example is that of regression, right? I have a bunch of points. For example, prices could be house prices, house price, and on the x-axis you have year, right? So all of us know that there was a kind of possibly not necessarily super linear, but at least an approximately linear growth in the house prices until a particular point of time, and things flattened. And in fact, during COVID, there was also a recession, big recession. So most often what people try and do is fit for the y, which is the house price, a function in terms of the x. Now in this case here is x, but you could have a more wider range of x's, and the x itself could be viewed through the lens of what we call the feature features phi. So what you try and do is approximate y using some feature mapping on the x along with associated weights w. I hope everyone understands this notation, right? This is basically a vector. Phi of x is a vector. And by default, vectors are shown as column vectors. W is again a column vector. So phi transpose is a row vector. Phi x transpose is a row vector. And row times column gives you a scalar. So what has happened in deep learning today is the boundary between the phi's and the w's have also kind of faded. Right? You have weights intertwined in a network along with feature functions. But for the purposes of this class, phi x would always be treated as something that is known, right? Either it is a known set of functions, or it could be nested. You could have one phi applied to another phi, as we'll see soon. And most of mathematical modeling is about learning the W. So as you see in the expression out there, you're trying to minimize with respect to some bunch of observations, xi, yi's. Okay. The difference between yi and the dot product. This W itself, as you see here, is a vector. Now, why are we interested in minimizing? Well, you would like to ensure that there is as close a match as possible, if not an exact match. But what you see here in the expression is not just the sum of squares of the errors, but also the lambda W square or lambda norm W square. And that typically is rationalized as regression, right? You've heard of how people are interested in, as rationalized as regularization. Okay, so this is often called a regularizer. Why is a regularizer used? To prevent overfitting, right? So you don't want the model to just memorize for your given bunch of inputs, y1, x1, y2, x2, etc. But you also want it to generalize to a new input x new. In this course, of course, we'll also see a different twist. The regularizer also plays another role. And that role is the role of, from an algorithmic perspective, right? Trying to bring in something called strong convexity, better convergence. Okay. So what you see in machine learning, which has some motivation, there is also often a counterpart in optimization. Okay. More about that as we progress. Another kind of, so this is to give you an example of why this course is important. Another example, it helps you formulate nice optimization problems, right? So I've given on the slide an example where I'm trying to build a speech recognition model. So let's say I have built an automatic speech recognition system. It's ASR. And let's say it's for accented English. I have good representation of, let's say the system has been built on, here's an example I provided, say some pure Tamil accented English, Malayalam accented English. Okay, so there's a mix of speakers, which also includes some Bengali. And now let's say I want this to do well with people with say background in Tamil who have also were based close to Kerala, right? So there's a district called Palakkad, which where the Tamil is very much influenced by Malayalam. So what if you want to do ASR on a mixed hybrid set? Or imagine I have the ASR already for Bengali accented, but then I want this to be adapted to Assamese, right? Now, what I've shown there is basically this blue box, right? Which has this box has a bunch of points. So if I want to adapt a model for a particular accented data, I might want to look at the neighborhood in that space. Let me give another example on the right hand side, which is easier to relate to, and then we'll go back to this, right? So imagine I had to identify points in this classroom where the bulbs should be turned on, where illumination should be turned on, right? So what would I look at? I would look at which are the bulbs to turn on will depend on what the occupancy is, where are people sitting. What else would I look at? Class should be uniformly illuminated irrespective of how many people sit there. Not correct, right? I mean, yes, what you would like is some kind of continuity in the space, right? So you would like some, so that people sitting, lots of people sitting here, maybe the lights in the neighborhood row should also be turned on. You want coverage. You want all areas to be covered. But if I had a budget, if I put a budget and say I can only turn on 10 bulbs, then you immediately also try and ensure that there is some amount of coverage in all the regions where people are sitting and not just the most populated region. So coverage is in pockets also, not necessarily monolithically throughout the classroom, right? So that's what I've tried to show here, right? So if I have the yellow thing is like the illumination. Sorry, yellow is the occupancy, right? So the blue ones are the bulbs. So I will turn on those bulbs which are representative of the occupancy. Likewise, if I have I have a test set of speakers and I want to make sure my speech recognition model is doing well, what would I do? So I'll have a similar analogy, right? So think of this is Tamil accent, this is Malayalam accent. And if I find that my data is in this space, or even more glaring would be something in this space, right? Which is that intersection of these two, then I would like these points to be picked up. They're the neighborhood points. And if I say I can train my model or fine tune my model only with say 1,000 examples, and I would like to make sure that 1,000 examples are as far as possible in the region of Tamil and Malayalam. If I want to do a model that does well in that space, right? So this is an example of discrete optimization, right? Selecting subset of points, but it has to be done in the context of the overall ML model. I mean, if you had an ML model such as regression, or rather a regression model with its corresponding loss, I would like the subset of points to reflect well on the loss, right? And not be selected in isolation. Okay, more on this as we proceed. So one is mathematical modeling, the other is computational optimization. So if I am running an algorithm and I want it to do well, right? I want to make sure that it goes or converges as quickly as possible and converges close enough to the objective in hand, right? So regularization, right? So regularization, for example, some of you pointed out, avoids overfitting. But in reality, it also improves the strength of the objective. So that algorithm, such as a gradient descent algorithm, can converge faster. Okay. So strong convexity to this kind of regularizer, which you see on the right hand side here, makes a simple algorithm like gradient descent converge faster. Okay, that's the other perspective, computational optimization. Is this clear? These two perspectives. Any questions? We are happy to take questions at this point. So two perspectives we have seen so far are modeling and computational law. Okay. So one might argue, well, by the way, with GPTs, software engineers can write ML applications with a few lines of code. And most people will argue no code even required. You just need prompts. So why do you need code? So why do I even talk about convergence? Why do I talk about modeling? And the chat GPTs of the world will give you the objectives that you can play around with. Well, not just that, right? The thing is, even if there is a chat GPT out there, it is basically a GPU guzzler. You're burning a lot of electricity, and there's a lot of effort to make these models more efficient. How can you make them efficient? Unless you innovate on optimization front, and unless you innovate on making parameter learning more efficient, right? And the other point is in operational deployment scenarios, like let's say an edge computing requirement. Often you don't even have access to a large amount of compute. So you'd like to make sure that the models trained can operate in very frugal environments. So that's the second point. End user requirements, you'd like models to behave in a way that is predictable, that is useful. So optimization plays a role there. And the third is, even from a consumer perspective, right? You need to at least be informed in the choice of objectives and algorithms, right? You don't want a next generation of just consultants. Enough. I mean, I know IT students do get paid very well by consultancy firms when they go for placements. But you don't want to create another genre of consultants who's just consulting on the right choice of optimization objectives and algorithms. We would like to be informed ourselves. So these are some counter arguments. If you have more counter arguments, do present. Right? The first argument against this course, right? Being I was trying to play the devil's advocate, is why would you need it? There's no need to write programs even. I presented some 3 arguments. Anything for or against? Do you all buy these arguments? That's possibly why you are here. So I'll let you speak whenever you want. The second argument is open source libraries can let you write. Okay, fine. I can write code, and I'm adept at writing code, but there are a lot of open source libraries. Why can't I just choose them, right? Why can't I find the right combination with practically zero knowledge of ML? Well, again, I want to highlight what I said just some time back. It won't help because ultimately you'll have to pay for the compute that you use. And you'd like to optimize for the payment and be effective in the spend that you have, right? And more importantly, we all want to push the boundaries of research. How many of you think that research in the ML space is completely saturated? Any of you? I'm happy if you don't lift your hands. That means you feel value in such a course. So yes, this course is also to push the boundaries of research and not be convinced that the solutions being sold out there are sufficient, right? The ChatGPTs, we need alternatives which democratize AI, which make it possible to use AI in very resource constrained settings. There's tremendous, misuse of, or rather, wasted cycles associated with the GPUs that are used to pre-train large language models, right? Of course, there have been recently a lot of social media posts also about making LLMs effective. I probably would have seen some from China. Something also came from Meta. Uh, right. Okay, so optimization is still considered one of the most important backbones of machine learning. So summarily, look at statistics, optimization, and matrix algebra. Even today, right, with the proliferation of tensor-based operations, you'll find that matrix algebra has to be backed by statistics, and what brings them together is optimization. Okay, so now what are the different flavors of optimization? The first is continuous optimization. I tried to give you a flavor here, the simplest problem in the form of regression, but classification, many others. And continuous optimization problems are actually can be viewed as relaxations. Right? What I would have ideally liked is an explainable model which says, well, why did the house price dip, right, around 2020, 21, say, right, post COVID? I would like some explanation. If there's the pandemic and something would happen, but for lack of sufficient data, because if you really want to come up with discrete rule based regression, you need infinite amount of data. So you relax, because in a relaxed space, points, 2 points which are far away, suddenly you can start measuring the distances. So continuous optimization, therefore, can be often viewed as an approach where you relax risk, error minimization, and so on. And here you have two flavors: supervised and semi-supervised. Now there's also unsupervised, primarily supervised and semi-supervised. Semi-supervised, unsupervised, we start looking at all of them in one big basket nowadays. And there's of course a third flavor, which is the reinforcement learning. So let's try and understand the simple extension of this kind of regression model when you have unlabeled data. So imagine I was trying to do this fitting, and suddenly some people told me, well, by the way, there is also a third dimension, not just the year, but also location, right? So, of course, my feature space has got richer. But what I also give you in addition to this third dimension is a lot of data about year and location, right? So-and-so person located in, or these many people migrated from one state to another state in this year, right? In those cases, I don't have the house price. So what I've done is added a dimension, and in this two-dimensional space, I give you a lot of points. Will that be of help in predicting house prices in those regions? How many of you think there can be some value? So you understand the scenario? I've just given you one more dimension, location, and a whole bunch of points, people who moved to a particular location in a particular year. Is that helpful in predicting potential house price? Why? Yeah, so you have now a preview of the demand, right? So this preview of the demand, right? Demand preview. This can give you another signal to potentially determine what the house prices could be. And this can be a lot of data, right? I may not have house prices for as many points as just the locations and the years. So this is what has made uh, large language models so effective, right? The effective use of a lot of unlabeled data. And what have we done there? Well, we have said one way I can slap on an objective, right? I've added one more component objective. So S is the one in blue is the supervised collection. The one in pink is what we call unsupervised, or I call it self-supervised collection. And one objective I try to slap on there is said, well, there was already this component, but based on this demand preview, I'm going to say, well, learn this W such that when I try and predict the yi, this is imputed yi. So imagine that based on this imputed yi, I try and predict. So my yi is an imputed prediction based on the w's. Now, of course, your question could be, how do I even So here's an example. So support vector regression was very popular until, of course, the tsunami of deep learning hit, right? The entire ML community. So support vector regression, what does it do? It says, well, instead of trying to fit this model, the regression curve on all the points, I will try and fit the curve on a subset of points. And the subset of points that I try and determine will be what we call the support vectors, right? So that was built into support vector regression, right? So here example was, instead of S, I'm looking at S hat. Now support vector regression did it very differently, but a naive formulation is to say, well, give me a subset S hat of S and the corresponding weights W such that the regression fit on S hat is as good as possible, right? So this is further adding a discrete optimization flavor to an existing semi-supervised, combination of supervised and unsupervised learning. So this is what kind of I was referring to, mixed continuous and discrete optimization. Of course, there are many other flavors. There's also clustering. So clustering is an example where you're doing mixed, discrete, continuous optimization. I talked about segmentation, but clustering would mean, okay, I try to find centroids along with the points that belong to that centroid. So there are two things going on. Locating the centroid is a continuous optimization problem because the centroid can be right, in the middle of the entire space, any Euclidean space. But then membership of points to those centroids is a discrete component to this optimization. So with this background, yeah, as I said, a growing number of problems are of this last flavor, right? I just repeating the same problem, determining locations for fitting bulbs along with intensity. So I've added one more twist to it. I said, well, if I want to not only locate the bulbs, but I also determine which bulb should be turned out to what intensity. So again, another flavor of an optimization problem, which is both discrete and continuous. And by the way, this bulb fitting problem is so canonical because it's pretty much easy to extend this to data subsets selection, right? So imagine these bulbs are basically the points that need to be sampled in training a model. Right? So you can also have intensities associated in terms of how often you want that point to be repeated. That's what curriculum learning is about, right? Curriculum is about learning which points to take first in training models, how much weightage to be attributed to those points, and in spaces such as knowledge distillation, you also want to make use of these weights in distilling information while transitioning from one model to another model. Okay. Okay. So this is the final thing, right? Even if you don't implement new algorithms, you get the expertise to look at these algorithms and understand how they work. So there'll be theory that will be talked about in this course, but the theory will be such so that you get good insight into why algorithms work, right? The theory is only the first term of the Taylor series of practices by Thomas Cover. So we don't dismiss of theory, but at the same time, we don't oversubscribe to theory because, as all of you know, there's a lot of engineering that goes into making those algorithms work. A good balance, right? So we will focus mainly on the algorithmic aspects of optimization, both continuous and discrete. And there'll be a lot of focus on the implementation aspects of these algorithms. That is going to be largely through the assignments, seminars. The seminars are basically the assignments and the project. Okay. So any other comments on why you would like this, how you'd like this course to shape up? What do you expect from this course? Anyone else? I can seed your discussion with some example here. Right. So One is, I would be as a student interested in how gradient descent um, behaves, right? Gradient descent for convex functions, it's intuitive. It might give you, good convergence, but how does it really behave for non-convex functions, right? What about discrete functions, which are concave-like or convex-like? How do these algorithms behave? Can we develop algorithms for discrete objectives? These are potential questions. Any other questions? Any other reasons why you would like to take this course? Yes. Thanks. Sorry, machine learning. Okay, machine learning for optimization. um, you mean pose optimization problems as machine learning problems? Okay, that's interesting. Yeah, for example, mm, the bulb fitting problem could be viewed as uh, a continuous relaxation of a discrete optimization problem, and where I would actually try and learn a neural network. But our focus will be more on the former, which is looking at the optimization problems, the range of optimization problems actually you can create in the machine learning space, right? To make machine learning models more effective. That will be our focus largely. But let's see if there's a course project that gives you the other perspective, I'll be happy. Yeah. You directly have to learn the function itself. So he has another counter to what you're saying, right? He's saying if you have to pose an optimization problem in machine learning, what about the objective of that machine learning model? The objective you use to learn the parameters of that model. Yeah. So optimization will be inevitable in that case. Any other thought? Can feel free to interrupt at any point of time. So matrices and vectors you'll have to be super comfortable with. Okay. And while I'm not so insistent on the basics of machine learning, it's not a hard prerequisite. You can ramp up quickly, but there's no compromise on the basics of linear algebra, matrices, and vectors. And of course, you should have also got exposure to algorithms and programming in general. Okay, so again, this is a very canonical set of topics which I've put out here, but as the course progresses, we'll see which of these topics we want to spend more time on. But certainly, you'll need to understand the elements of convexity and the notions of subgradients, projected gradient descent. Because what you use extensively today are projected gradient descent and subgradients, and the processes of accelerating, which is super important. Momentum based. How did they come about, right? And also some Newton based approaches are again are again resurfacing. So second order methods in general. Some of the others I might just skip and give you optional slides to gloss through. Hopefully you find them useful for your projects, right? So the theory is in my CS709 convex optimization course. I will not do so much theory. It's going to be mostly practicals and the intuitions from theory. There's also be discrete optimization. In this offering, I want to do a little bit more on the discrete optimization part. While there's a significant grounding in submodularity that has helped discrete optimization, but there are also other areas, metroids, optimal transport, etc. So let's see how much we can cover those. But certainly the ones on the right, we will spend more time on. The submodularity, minimization, maximization, and practice. Okay, those are parts 1 and 2, but parts 3 and 4 are very critical for this course, which is seminar and projects. So what we have done, and I think we have a couple of members who have come from our team. I'm going to have these projects largely based on LLMs. Okay, and let me do the following. Let me just screen share this. This is a link from. Okay, so this is the link. you can go to this link, bit.ly CS769 course paper 2025. So to make this course relevant and yet impactful, the projects are all going to be largely as part of this Bharat Jan initiative that I'm leading. A lot of meta research and project summaries and progress has been organized thanks to the TAs and also the Bharat Jan team. Is Durga here? Yeah, Durga is here. So Durga, Priya, maybe you can just come up here. Pratik is unwell, so he couldn't come make it today. We also have a couple of others from the Bharat Jan team who will help you. Yeah, so we have also Vishal. Vishal will also help you. Skundeshwar is not there, right? So we have some members of Bharat Jan and some members who are students here yet. So Priya is a student; she's a TA, whereas Durga is leading the text foundational model training at Bharat Jan. Thanks. So the broad threads are optimization on architecture, optimization on data, and algorithm optimization, all in the context of LLMs. While we have trained our bunch of foundational models from scratch, we'll make them available, right? We don't expect you to do pre-training from scratch at scale. So that's not expected. The expectation is to look at some of the state-of-the-art architectures and assess them on small representative samples. And then the Bharat team can take it forward because we can't afford to give you too much compute. So certainly, 1 or 2 GPUs for some time, couple of GPUs if required as project teams. And even then, you'll need to warrant your usage of the GPUs based on proper grounding in theory and understanding of the papers. Therefore, the seminar is going to be closely tied to your project, right? So your seminar will give you the grounding required so that you're well prepared for the project, but largely along these 3 lines. Okay. So now, if you navigate, are you able to access this link, this tiny URL, everyone? So you can go through this sparse beta reweighing for LLMs, early exit with knowledge distillation for LLMs, pre-training efficiency for LLMs, then the emergence of skills via grafting. So as LLMs are trained, how do you make a custom LLMs through emergence of skills using approaches such as grafting? Matformer is another very interesting architecture that came out from Google. So how can you have a new efficient transformer architecture? So of course, new architectures are also welcome, but there has to be proper rationalization. So permutation matrix subset learning. So basically the subset of data points on which you do the pre-training, can it be learned through a permutation matrix? So composition of submodular functions. To give you the curriculum, I talked about the curriculum, the sequence of points through which you will actually learn an LLM. Can that be done through a composition of these discrete functions with diminishing returns? Neural optimal transport for curriculum learning. So obviously, we will not be able to we may not be able to cover optimal transport. Some of this you have to pick up, right? That's why my best effort would be to give you a good flavor of the optimization problems, the way you study those problems, but ultimately you'll have to do significant reading yourselves. So again, in the space of optimal transport, the core set, identifying a core set of points using either synchron. So synchron basically gives you excellent regularization, very good convergence, right? So we'll get some glimpses of why that happens through L2 regularization. But you'll have to pick up some of this. Now, how can this be used for identifying core sets or task vectors in Riemannian manifolds? So increasingly, these models need to be trained on multiple or fine-tuned for multiple tasks. How do you kind of cross-pollinate across tasks? There's a space in which these tasks exist, right? So Riemannian manifolds give you a way of navigating through that space. Or adaptive submodularity for LLM architectures. Right? So far we talked about fixed architecture, but how do you play around with the LLM architectures themselves? But let me be very honest, you need to be absolutely serious about these projects, right? We can't be burning GPUs with inattentive reading of papers or their understanding. Okay, of course, in many cases, the papers themselves might not be very well written, which is understandable, right? Um, and then catastrophic forgetting using gradient subspaces. So this catastrophic forgetting is where basically, as you keep training the model, it just starts forgetting what it has learned on earlier. Now, is there a way we can characterize this forgetting itself, anticipate it? See, that's very important in ML. Before you run an experiment, you should anticipate something. You can't just say, well, if the question is, what has happened to the experiment? I have no idea. We're waiting. That is not an acceptable answer. Right? Insight should be sufficient that you start anticipating. So, can we anticipate catastrophic forgetting by understanding gradient subspaces? Um, core sets. Okay, so there's a whole bunch of papers on core sets and curriculum for LLM training. Durga has put in a very interesting project on how these a bunch of projects, a bunch of papers on making LLMs generalized enough, right? So there's been a recent release when I was with Jan Leekand last year. And one of the main points of discussion was how LLMs could generalize better, right? And he gives us favorite example of his that you don't need a zillion images and zillion parameters to predict satellite orbits, right? You do that using 6 or 7 parameters. So he expresses firm conviction, and we have in fact been doing the similar work for Indian languages, that you don't need so much of textual data to learn models. So they recently had a paper called LCM, large concept models, right? So that was an effort towards generalization. There are more. In fact, Durga, we can add LCM also to this list, right? So how do you make these LLMs generalized by design, right? And there are a whole bunch of papers on optimizing the data set for multilingual translations. Right? So if you want the models to, well, basically multilingual representations. Instead of translations, is representations. So Indian languages do have a lot of commonality, right, in the way their vocabulary, their grammar. Can that be used again by design for effectively learning multilingual LLMs? Okay, and there are a whole bunch of more papers you'll see. We have not completed it. The list is keep growing. Will keep growing. For example, how do you make good utilization of book repositories, which are books for training LLMs? Because the books have a lot more structure, and not only that, they also have the layout, which is very informative. Right? So there's of course a group in BharatGen. We are trying to build document foundational models, which we haven't seen around. But this is more specifically about high quality content leveraging for building LLMs effectively from books, identifying subset of source language instances for labeling. So if you Indian language, there's less than 1% data represented uh, over the internet. So how can less not be a roadblock, right? That's another question to be answered. While Jan Leekand they tried to do this JEPA and LCMs, like the large concept model, can we do that for Indian languages, right? So this is another very important topic. There'll be more topics that will be coming up soon. A lot more on instruction fine tuning, right? Again, a lot of black art exists in the process of instruction fine tuning the large language models so that they respond to user queries, so that they perform well on downstream benchmarks. If you've heard of RLHF, DPOs, right? Those are all optimization frameworks that have emerged. But are they the end of the road? By no means. Right? When I have a model producing an answer, how do I rate one answer to be better than the other from every perspective? Because there's no absolute preference, right? It's all relative. I might prefer X over Y because X is more factual than Y. You may prefer Y over X because Y has better coverage and attribution. It makes you think. Y makes you think. X doesn't make you think. So you see, multiple perspectives exist when we are ranking results, when you're giving feedback. So we'll see more of these coming up soon. But I think this, I hope this gives you a preview, right? So this is all in the repository. So team of 2 to 3, you can pick from those topics. If you want to suggest a topic, please do, but there has to be sufficient rationalization. A lot of effort has gone into rationalizing the topics that have been listed, right? Until last year, so if you have your own compute, you can, right? You can come up with your own fancy problem. But to leverage the compute that we are going to provide, you'll need to fit into one of these. And it's a fact that each of them itself is quite rich, right? There's enough rich set of topics you can choose from. Does that help? Any questions? So you need to create teams of 2 to 3, max 3. Okay? In my experience, the fourth member in every team is vacuous. I've never seen a 4-member team where the fourth member made good contribution. Okay? I'll be happy to be proved wrong, but I'm completely against a 4-member team here. 3 is the limit, in my opinion. Okay, so you need to scrutinize the paper, how it connects to the broader scheme of the topic. And there'll be one team presentation per week post midsem during lecture hours. And the other teams are expected. So this is, as you know, this, see, you need to be in this course because you really want, you care for optimization in machine learning, right? You want to make a difference in this space. And I'm sure, India can, through India AI mission, through initiatives like BharatJal, make a big impact. But unless you feel for this, it won't happen. So while I can put, must and should and so on, ultimately, it's important that you resonate with the papers that are being presented by others, so that collectively there is a lot of useful output we are producing. Right. So one way we want to do that, we'll certainly do that, is there'll be written responses anticipated. In fact, we didn't do this last year, but this year, after every presentation, there will be a discussion. There'll be a discussion. I'll actually put some questions. In fact, every class that I put, I'll have some points for discussion. So I'll put out a Google Doc, and you can with your authorship write comments. See, I would like to see collective wisdom evolving, especially for those projects, but also for each class. That's the written responses for each. So in preparation for the classes, I'll try and put up some write-up for each class. Okay, so summary of the points discussed and so on. And the projects will be basically based on the papers that you present for. So the project is a follow-up, right? As you saw, each of those topics had a listing of some papers. So the paper presentation would be a part of this seminar, and the project would be implementing, baselining, right, and so on. And then you'll get help from our BharatJal team. Durga, if you can move on. It was just to introduce. Thanks, Durga and Priya, for being here. If you have any questions, please do ask, because they have too many things on their hands, so they stayed for too long already. Any questions for them? They're both TS, Vedant. I'll list their names, but if there are questions for them, please ask. Thanks. So the relevant books for this course. So by the way, project and seminar cumulatively will be almost 55% or 50% of this course. Okay, so take them very seriously. For this course, what are the relevant books? I'll be posting all of them on Moodle. My notes on convex optimization. In fact, not just my notes on optimization, I'll also be putting a lot of notes, my own notes. So for example, these are notes on, by the way, Pratik is online. I don't know if you can hear Pratik. So Pratik, if you want to share something, please do share. He isn't keeping well. So I'll also be sharing my notes on word embeddings, all leading to LLMs, the transformer architecture, and so on. Yeah, so I mean, I'll share this as well along with my other notes. So my notes overall, and then so there'll be a lot of notes. My focus, of course, in the notes will be how the optimization flavor can be brought into each of these models, ranging from word embeddings to recurrent neural networks to transformers to GPTs and so on, right? To RLHF and so on. There are a couple of other books which are very, I would say, very foundational. Just not sure how much the community today considers them foundational, right? But had it not been for all of these legendary pieces of work, I don't think optimization would have been effectively used as it is today. So specifically, a course on combinatorial optimization, learning with submodular functions by Francis Backup, very nice piece of work. So is the Sebastian Bubeck's course on book on convex optimization. I love them. Okay. Now, the remaining part of today's class, we'll try and we'll delve a little bit into some of these optimization problem flavors. I will not go through all of them. Some of them we'll go through today. Okay. So supervised learning, I give you a flavor for least squares, but a little bit more today. Logistic linear regression and so on. Unsupervised k-means clustering, principal component analysis and so on. Then contextual bandits in the form of softmax estimators, policy, exponential models, and finally recommender systems. In fact, what I'll be doing, just give me a second. So let me, in fact, I have. This again. Just a second. Yeah, I forgot to present this. So there'll be 20% mid-sem exam, 25% end-sem exam, 35% project. And the project is going to be super critical. Anyone who does well in the projects can qualify for an A grade. But as I said, unlike last year's course, this year's projects and the seminar presentations, there will be a lot more interaction. So I'll, in fact, post questions, post the presentations, and expect team to all to interact. Okay? So that's going to be very important. That's why the increase in the grades, the responsibilities also. So increase in the percentage weightage, responsibility is also higher. Please do you join MS Teams with this code. If you can please make a note of this. C, small c, small n, small s, small j, small v, 56. And we'll organize all the content on Moodle. So how many of you are on Moodle already? Okay. Okay, so the TAs are Prateek Chand, Priya Mishra, Suraj Pracha, Vedant Goswami. Okay, so any questions on this? Just give me 1 second. Okay, so if there are no questions, then the continuous optimization in machine learning, I said that there are these 3 canonical problems, right? Canonical examples. But how do they manifest today? So they manifest today, for example, in supervised learning as fine-tuning of deep models, fine-tuning of LLMs. The way the unsupervised learning today manifests is pre-training of deep models, the pre-training of the LLMs more generally. But what we'll do is take these canonical examples of logistic regression very quickly, a breezy, right? Just so that you know, these are these canonical examples of uh, underlying either the supervised or unsupervised approaches. For example, K-means and principal component analysis underlie a lot of the concepts behind the pre-training kind of approaches. Or reinforcement learning from human feedback, agentic systems, DPOs. Underlying all of that is, contextual bandits from reinforcement learning. So some glimpses into this will help, okay? So that you don't get overwhelmed by the complexity of these large models. Rather, you see the optimization problem and its motivation um, in a way that's disentangled from the large architecture, right? So the big picture, if you look at the big picture, you have this big continuous and discrete optimization. But each of this continuous optimization and discrete optimization are themselves very large spaces. A small subset of the continuous optimization is this convex optimization, right? And linear programs, quadratic programs are even smaller subsets there. Likewise, for a small subset of discrete optimization is a submodular optimization, which has again, linear. Linear is always the simplest case, whether it's discrete or continuous. And I've given some examples here, right? So deep neural networks, LLMs, all of them are in this space, continuous optimization. On the other hand, discrete optimization is often viewed as a subroutine that gets invoked, whether it's hyperparameter optimization, network architecture search, right? Or whether it is identifying data subsets. They are often critical to make the continuous optimization versions more effective. They're complementary. Of course, as things progress, and I hope some of us define what the future is, we'll see a lot more seamless interaction between these spaces. I'm pretty confident about that, because I feel there's too much of a silo today. Okay, so I have already told you about this breakup. I gave you some time to think about it, but if you have any more questions, please let me know on this course logistics part. Okay. So little bit more on the course projects. I already gave you the seminar and paper list, but you could also, the encouragement is to contribute to Bharat Gen, but there is also an open source platform before Bharat Gen called Decile, decile.org, which is for data efficient learning. Again, that's an example of what we have developed over years. And if you go to this video talk and panel discussion, you'll see a lot more on that. Sorry, overview presentation at Decile as part of my first talk. You'll see a lot more on Decile. But I also presented an overview of the kind of progress we have made in Bharat Gen based on data efficient learning and computation. So this is a little bit more on the project so that you get a context beyond the list of the projects themselves. So Decile is this data efficient learning platform. Right? And it has these multiple modules, core sets and data subset selection, deep diversified interactive learning, submod lib, semi-supervised data programming, and so on. And then finally, targeted subset selection. Okay, so more as we progress. Okay, so having done this course logistics part, as I said, I'll have a breezy introduction to some of these canonical examples. Supervised learning, clustering, principal component analysis, and so on. And I will, while the motivation can be all LLMs, right? Either fine tuning or pre-training or RLHF, we'll need to still understand the bare bone, right? The bare bone optimization problem. What does it look like? Right? So those canonical examples will give you this bare bone exposure. Okay, So let's take the first one, which is supervised learning. We are given training examples x1 to x1, y1 to x and yn. Could be the y's could be spam versus not spam. Could be handwritten digit recognition, where you're trying to say, well, is the digit 0 or 1 or 2 until 9, or house price, which is an example I started today's class with, right? In the case, why I showed the regression example, in the case of classification, you're just looking at plus and minus, right? Or you're looking at multiple classes. In the case of digit recognition, 10 classes. So how do you model this? You'll start with the inputs xi, slap some function like phi and make it phi of xi, and then take some linear combination or some non-linear combination. So the linear combination is W transpose xi, but what we often do is subject this W transpose xi to a generalized linear function, like a sigmoid function. Okay, so this brings us to the more general representation. The model is f theta x, theta is the parameters, and in the case of deep models, you have f theta 1, theta 2, theta l, where you have a nesting, right? You have f1 applied to theta 1 transpose f2, which is applied to theta 2 transpose f3, and so on until theta l minus 1 transpose fl. So the nesting that typically you see in deep networks. You can often replace this thetas with w's, right? So the thetas and w's will be used interchangeably in this course. And the loss function measures the distance between the f theta, the composite f theta for each point xi and its yi. And as I said, in the generalized linear function, you also apply, you could the final f1, for example, you could be, in fact, any of the f's could themselves be some sigmoid kind of functions, activation functions. Okay, and the loss function tries to measure how far this f prediction, capital F prediction, is from the y's. The distances themselves could also be probabilistic. Okay, so for example, instead of saying I'll measure the distance like this, I might put a KL divergence. I might say, well, I want a KL divergence on the P of y, from, let's say, a posterior based on the W. Where you're looking at the distance between the distribution based on the data, the empirical distribution, and the model based distribution. So the distance need not be always L2, right? Keep that in mind. Okay, so I've given here a simple Colab notebook, right, where you can get some exposure to the. So I'll try and do that wherever possible. The different elements of linear regression, which should be possible for you to understand very easily. Sorry. What happened? Yeah. So we have so we have started with a single variable regression exercise, and we tried to fit the model. So these are the points, and we've shown how a gradient search starts with something which is totally off and then converges, right? Become very feasible because of not just gradient search, but also because some of these problems are amenable to closed form solution. You can find closed form solutions as well. Okay, so here we show the ordinary least square solution. What is interesting is you can find a closed form solution as well, the ordinary least square loss. So what I try to show here is, right, in this case, the validation loss for a function 1, so 3 plus x square plus x, 2x plus x square plus 2.5 x cube. Okay, this is the complex function. And here what we have shown here is a least squares fit based on a linear interpolation. And you can see the red line is totally off, right? So what you do in practice is, well, you say, well, if I have to fit, I will not take the raw x, but I will subject it to a phi, some kind of non-linear transformation. Let's say through some polynomials. What would I do here? For example, if x is a vector, this phi, to get a curve like that, I'll say I'll make it xi plus xi square, sorry, xi comma xi square, comma xi cube, and so on. Right? Specifically in this case, because the original function had until powers of 3, I mean, I have the extra information, therefore I'm able to take it until 3, right? So this gives me a better fit. You see that? Is this visible from behind or no? Okay. So I've enlarged it a bit. So we have coded up gradient descent here, right? And you can see the fitting. But the problem is, as we'll see, there's a problem here as well. But before we see the problem, there is also another interpretation. There's another interpretation is which basically it is a probabilistic interpretation for linear regression, right? Now, if this kind of curve, right, this kind of curve is fitted so tightly, if I give a new point here, the issue is that this curve would have overfit, right? In this case, well, the red is mimicking the green. But imagine that instead of xi cube, if I had taken higher powers as well, right? xi4, xi5, the red curve would have become a lot more wobbly, right? It would try and fit as many points. So here it is trying to compromise and not fit all the points. So, so what we see, there's another collab which I'll show, is putting the Bayesian interpretation. You put a prior. You say, well, I would like the fitting to happen, but with the understanding that the weights associated with the higher order terms should be small or should just go to 0 or vanish. That's a prior. I'm saying that I don't want very high degree polynomial, right? So that can be reflected through a Bayesian prior or equivalent through what we call regularization. Regularization is just a way of putting a prior, saying that I don't want the W's to have unbounded magnitude. Right? So, yes. So it turns out that for a particular kind of prior called the Gaussian prior, on the parameters, not on the data, the parameters, this L2 regularization is equivalent to a Gaussian prior. Okay, it's equivalent. So if you had a different kind of prior, let's say the Lidstone prior, then that turns out to be equivalent to using an L1 regularization instead of L2. So they're equivalent modulo the exact form of prior. But anyways, the goal there was to show that the loss plus regularizer framework has already two motivations. One is to avoid overfitting. But instead of saying I want to avoid overfitting, because overfitting looks like an afterthought, right? Something has gone wrong, so I slap it. The second perspective is I put a prior. A third perspective, which we'll also see in this course, is, as I said, to make the objective better behaved. So it's interesting, right? This is science, that the convergence of multiple perspectives, multiple reasoning into one framework. So that should excite us, right? We still, I mean, even with LLM, I hope people remain scientists, right? And are introspective as to how these models behave. So the loss plus regularizer framework is largely this: L plus S lambda times omega, right? And as I said, the purposes of regularizer we already saw, to increasing the bias of the model, to yield a theta that are simpler, so that the model doesn't become overly wobbly, right? That's what I was trying to show here. We already saw from a straight line it became quite curved, but I don't want it to keep on becoming more and more curved. That's one purpose. The other is we'll make the optimization problem well behaved through properties such as strong local convexity. There are also other properties: Lipschitz smoothness, Lipschitz continuity, and all that. Okay, so now we see a whole range of different kinds of losses. So logistic loss, hinge loss. So what is logistic loss? It's basically when you have a distribution on the class yi equals C1, yi equals C2. In this case, just tool yi equals 0 or 1. And I would like to maximize the likelihood, right, of the class labels that I see in the data. So the logistic loss, which of these curves is a logistic loss? Anyone? Yes, can you do a match the following? Which of this is the logistic loss? The red one, the blue one, the green one, or the black one? Yes? How many say the red one? Anyone for the blue? Okay. What about the hinge loss? Which curve? Okay, the green one. So what is the hinge loss doing? It's looking basically like the margin at the margin, right? I'm saying my f theta, if I'm trying to fit, instead of trying to say all the yi should fit, I'm saying, well, the fit should be reasonably spacious, right? That's what we are trying to do. Which of them is the one? The green is the one, right? So hinge loss is again used for classification, not for regression. Well, hinge loss can also be used for regression, but what about this class? This loss, softmax loss. So what is the x-axis? Y into fx. Yeah, thanks for asking this question. What is the x-axis? Y into fx. So softmax loss is again used for classification. Which of these curves is softmax loss? Well, it is basically a generalization of the logistic loss. Right? So you can consider the softmax loss to be again the red one. Absolute error. Which curve is absolute error? F theta minus y, the absolute distance. Yes. Sorry. The green one. But I thought you said the green one is the hinge loss. Right. So let me. Right. So the red one is certainly the logistic loss. The hinge loss is indeed the green one. Right. A hinge loss you can see is hinged at 1. That's why it's hinge. Softmax loss, as I said, is a generalization of logistic loss. The absolute error and least square error are not necessarily shown here. Okay. What you seen in the black one is the step loss. So what we have seeing in the plot is only the classification losses, not the regression losses. So this is the intuition I want you to develop, right? Okay, you don't, even if you don't have the entire ML background, you should be able to quickly eyeball and identify which loss corresponds to which objective. See, all these three losses in the case of classification are trying to approximate the step loss. What is step loss saying? Well, if you have the correct class, the loss is 0. If you have wrong class, there is some loss, right? 1. So you can see the hinge loss is trying to approximate it, the step, using something that is continuous. May not be differentiable everywhere, right? The green curve is continuous, but not differentiable at the point 1, where the x-axis is y into fx. I hope you want me to enlarge this? Okay, I can't enlarge it. I hope it's visible. Um, so absolute error and least square error are pure regression losses, and they are not depicted in this curve. But you can see that the least square error, how would it look like? Least square error. How would it look like if you were to plot, say, y into fx? Well, will it make sense to plot against y into fx? Because y is when it's plus minus 1. Then y into fx makes sense, right? As for classification. So you would actually not plot y into fx, the pure regression losses against y into fx. But you would expect a quadratic kind of curve with respect to the weights. Okay. And then the regularizers, L1 regularizer, we didn't discuss. We discussed only L2 regularizer. By default, when we say L2 regularizer, we are basically saying you're taking a summation of the squares of all the components of the weights. L1 regularization would mean what? Sum of the absolute values. Okay. The other interesting thing is from a regularization perspective, right? I mean, why am I putting it as a plus lambda omega theta, right? I could have actually done the following. I could have said minimize the loss L, right? Minimize this L such that the omega theta is less than or equal to some gamma. Basically, in this case, it's like saying that find me the weights, so minimize the loss such that the weights are within some sphere or a circle. Now, if you adapt that view, right, then basically you're saying in L2 regularizer, they should be within the circle, right? You can say the pink circle. What does L1 regularizer mean? If I put omega theta is less than or equal to R, where omega is this sum of absolute values, then you're basically saying that the point should belong to one of the corners. So we'll see from even optimization perspective why this gives you sparse solutions. Very interesting, right? Many of you would have heard, right? L1 gives you sparsity. Why does it give you sparsity? We'll see from an optimization algorithm, from algorithmic perspective. Sorry? So that at least you get one of. So why do you need sparsity? Well, one big area in large language models is quantization. You want models which are small, compact. In fact, so compact that you can sit on your phones. Now, how do you do that unless you identify a subset of the parameters which are really effective and cut the others to 0? It is feature selection as part of the model learning. So the question is it feature selection? Yes, but it's part integrated into the model training itself and not separately done. Right? So we saw this example today. I want to conclude with this last question. So which of these have closed form solutions? Closed form in the sense I can write down W star equals something, something, something. Which of these do you think? So I have L1 regularized logistic regression, which is using logistic loss and a L1 regularizer. L2 regularized logistic regression using logistic loss and L2 regularizer. Likewise, SVMs use a hinge loss and a L2 regularizers. Multi-class logistic regression uses softmax loss and a L2 regularizer. Lasso least L1 regularized least squares uses L2 loss and L1 regularizer. And L2 regularized least squares uses again least squared loss and L2 regularizer. Only the last one. Okay, somebody guessed, right? So only the last one, L2, which has a closed form solution. Loss plus, yeah, this is, so in fact, it has a solution. Theta equals x transpose x plus lambda I whole inverse x transpose y. That is its closed form solution. Right. And now the thing is, that's interesting from an optimization perspective. What happens is, as I said, right, there's always this something interesting happening from an optimization perspective. This lambda basically increases eigenvalues, is like increasing eigenvalues and bringing stability to the solution. It increases eigenvalues of the solution. Sorry, not of the solution, but of this matrix x transpose x plus lambda I, and therefore brings stability to the solution. Think of it as a surrogate to the Hessian matrix. Okay, so more about that later on, just to kind of tease your understanding. And yeah, as I said, the last one is the only one to have a closed form solution. But there are also many other combinations. There's only some combinations. You can have L1 variants for SVM and logistic regression. And most of them are going to be solved using iterative algorithms, which we'll see in this course. Okay, thank you. I think you have to get started looking at the projects, right? I think that's very important from day one. Start reading identify teams. Of course, the projects have to be exclusive. I don't want the same team, the same project picked up by two different teams. So, and you can please refer to the recordings of last year, because some of the use cases I'm going to really brush. Today, I would say I did this in a little bit more details. But we'll talk about autoencoders the next time, unsupervised loss. A canonical example of that, just like supervised learning, these were canonical examples. In unsupervised learning, which is for autoencoders, word embeddings, etc., and LLMs in general, a canonical example is principal component analysis. So we'll rush through that. One example for RLHF, and then I'll move to the course. Thank you.
R&D with learning, right?
Yeah.
So that's adaptive modularity. So how does that work with this course?